In this video, I will be using a convolutional neural network, implemented with Keras and written in Python, to recognize handwritten digits and perform basic operations between them. I simultaneously aim to give you an intuition for, an understanding of, convolutional neural networks and their awesome potential. I will start off with a demonstration of the program. I enter 13, one digit at a time, clicking Save Image after each digit. Then, I click Multiply, and enter 14, one digit at a time, clicking Save Image after each digit. When I click equals, I get the correct solution of 182. Pretty cool, huh? The core of this program is a convolutional neural network. Convolutional neural networks are loosely based on the manner in which all mammals perceive the world around them. This manner involves a hierarchical series of feature recognitions, starting off with simpler features like diagonal lines, curved edges, etc., and progresses towards complex or abstract recognitions, like combinations of shapes, and finally, the classification of entire objects. That's pretty simple, but how would you mathematically model this process? Let's dive deeper into how convolutional neural networks do what they do. Like the standard neural networks discussed in previous videos, convolutional neural networks involve input layer neurons, weights, biases, hidden layer neurons, and output layer neurons. However, they are also a bit different. Let's begin at the start of the convolutional neural network and work our way through it. Inputs are a 2D matrix for black and white images and a 3D tensor for colored images. By the way, tensors are just arrays with dimensions that are higher than 2, and the third dimension in a colored image is for the different color channels, usually red, green, and blue, in an RGB image. In our case, images are black and white. Next, weights are arranged into 2D matrices. This differs from a regular neural net where inputs and weights are scalars, or just single numbers. In a regular neural net, you simply multiply inputs by weights. How does this work with matrices or even tensors? Instead, the dot product is computed. Essentially, to perform the dot product between the image, which is a matrix, and a smaller matrix, which is the weight matrix and is often called a filter, you multiply the filter by each corresponding value in a section of the image, sum these values, compute the average by dividing by the number of values added, and place this in the corresponding position in the resulting matrix. You then repeat this process, sliding the section of the image that is multiplied, or the receptive field, until all the values for the resulting matrix are found. Note that this resulting matrix loses 1 pixel at its edges in every direction, and programmers sometimes perform padding, in which the lost pixels are replaced with zeros. When performed, padding could make the resulting matrices 16 by 16 instead of 14 by 14. Also note that initially, like any other weight, filters contain random values and are adjusted in training. Performing these repeated dot products in this manner is known as convolution. Convolution plays a central role in a convolutional neural network, hence the name convolutional neural networks. To understand why, let's take a look at 2 examples, one simple and one slightly more complex. I'll start with the simpler example. Say that this is the input image and we apply this filter to it. This filter can be thought of as a low resolution horizontal line, and look at what happens in the resulting image. Horizontal lines are kept, and almost everything else fades into a dark gray and is ignored. In this way, filters keep what is relevant and ignore everything else. What is relevant is adjusted based on the needs of the neural network in training. Mathematically, this occurred because the resulting value in the matrix was large if and only if the receptive field was very similar to the filter. If they were not similar, then the values in the image matrix were multiplied by values close to or equal to 0 in the filter matrix, or vice versa, making the resulting value small. So far in this video, filters have contained only positive values. This, however, is a simplification. Like in standard neural networks, weights in a convolutional neural network can contain negative values. For these 2 examples, when visualizing any values in filters, including negative values, I set the lowest value in the matrix to black and the highest value in the matrix to white. While visualization is a powerful tool, it is also important to consider the numbers, because the numbers are all that the computer sees. In this next example, I will use negative values in the filter and a more complex image. This is the new filter. While it looks exactly the same as the filter that was just used, it contains negative ones where there were once zeros. The image itself is more complex, with many details. In the resulting convoluted image, the horizontal edges are highlighted, and most other information is lost. The general principle of how certain values are kept or even amplified and others are ignored through convolution remains the same. That is, if the filter and the receptive field are similar, then the resulting value is large, and if they are not, then the resulting value is small. However, negative values differ from zeros in an important way. With the filter that was used in the first example, the values in the receptive field corresponding to the zeros in the filter don't matter. They can be 0 or any other value, and since any value multiplied by 0 is 0, the resulting value will be 0. So, with this filter, you will keep any horizontal line, regardless of what values are above or below it. When the zeros are replaced with negative ones, however, the filter will preserve a horizontal white line if it has low, or ideally negative values above and below it. This is because if the values above and below the line are large, then large values will be made negative, making the resulting sum smaller. Similar logic can be used to explain why a horizontal black line surrounded by large values will be preserved. Hence, this filter may look for horizontal lines making up an edge if the edge has a height of 1 pixel and is surrounded by values that contrast the line. This fact explains the emphasis on edges rather than any horizontal lines in the resulting convoluted image. In this way, negative values in filters allow the model to emphasize a wider variety of features. In a convolutional neural network, it is almost always advantageous to have multiple filters in order to highlight multiple different features separately, but more on how this plays out later. The next step involves making the output, after applying the filter, have a lower resolution, but still retain the most important features. The point of this is to make the neural network more efficient and less computationally expensive, especially during training. This step is pretty simple and is called pooling. First, you define a pool size. This will be the dimensions of a section of the matrix that you will compress into one value. Perhaps the most popular method of this compression is simply taking the maximum value, where the value represents pixel intensity. In a black and white image, which is what we will deal with, the value represents how white a pixel is. So, the network simply slides across the image, taking the maximum value in a certain area. Note that for both convolution and pooling, there is something known as a stride length. Stride length represents how much you move the window after performing convolution or pooling, in both the horizontal and vertical directions. For convolution, the stride length is usually 1 by 1, or 1 horizontally and 1 vertically, and in pooling, the stride length is usually the same as the pool size, which is the area from which the model takes the maximum value. Changing the stride length from the standard values is usually unnecessary, and importantly, will change the dimensions of the resulting matrix. Finally, we apply an activation function to all the values in the now compressed matrix. Remember, an activation function serves the purpose of allowing a neural network to approximate a nonlinear function, and this remains the case in convolutional neural networks. By the way, you could technically apply an activation function before pooling and directly after convolution. However, this would be slightly more computationally expensive as the matrices will be larger. These three parts, or convolution, pooling, and activation, can be repeated to further add complexity to the model. Note that you don't necessarily have to implement these parts precisely in this order. As an example, it may prove beneficial to perform convolution, activation, convolution, and only then pooling. What happens when you add more convolutional layers is really cool. Say that I start with a 28 by 28 black and white image, and I have 32 filters in my first convolutional layer. So, I now have 32 26 by 26 matrices, assuming that I don't perform padding. Whether I apply pooling and activation is irrelevant to this scenario. Let's say that I don't, and I add another convolutional layer with 32 filters. I actually don't get 32 times 32 or 1024 new matrices after I apply this convolutional layer. So, I don't apply 32 filters to each of the previously filtered images. Let's break down what actually happens. Each of the 32 filters will actually have a depth of 32, corresponding to the depth of 32 in the previous layer's outputted tensor. From this point, the dot product is calculated between the receptive field in the first matrix and the first matrix in the first filter, between the receptive field in the second matrix and the second matrix in the first filter, between the receptive field in the third matrix and the third matrix in the first filter, and so on. Then, the average of all these values is computed and is placed in the top left position of the first resulting matrix. Then the rest of the values in the first matrix are computed by sliding the receptive field across the matrices, computing the dot product, computing the average value, and placing it in the corresponding position in the first resulting matrix. So, the first resulting matrix was generated with the first filter. This process is repeated with each of the filters until there are 32 resulting matrices. Essentially, 2D convolution between a matrix and a filter is repeated to account for the depth of both the tensor and the filter. The average of these values is computed to make the result a 2D matrix, and this process is repeated with each of the filters. By performing convolution and averaging the values in this way, I combine the highlighted features in a computationally inexpensive way. By doing this, we add a level of complexity that will force the model to make progressively more and more intricate feature recognitions or highlights as it finds the optimum filter values deeper in the convolutional neural network. So, deep in a convolutional neural network, where convolution, pooling, and activation has already been performed quite a few times, a filter that looks like a horizontal line, for example, will likely result in the highlighting of a much more complex feature in the original image. Generally, by the last convolutional layer, each filter will represent a relatively complex feature. I say relatively because depending on the scenario, a curved edge could be a complex feature, like in our case, or an entire human face could be a complex feature. While all this may be slightly complicated, it is important to remember that at a high level, we are still just computing a product between an input and a weight, and because of this, eventually allowing the neural net to find the relationship between input and output. Then you flatten all the pixels into a single vector. Remember, a vector in programming is a one-dimensional array. You connect each pixel to a neuron in either another hidden layer or the output layer. Remember that by this point in the convolutional neural network, a pixel should represent the presence or absence of a relatively complex feature. In this way, we add a fully connected section to our neural network. This is done in order to take advantage of all the different features that have been learned. In other words, the section of a convolutional neural network with convolution, pooling, and activation performs feature extraction, and in the fully connected section, the network finds the relationship between the presence or absence of these features and the different classes. Like in the last video with breast cancer diagnosis, the output will be a set of probabilities. These probabilities represent the chances that a particular image belongs to a certain class, according to the model. You can then take the digit corresponding to the highest probability, and voila, you have a predicted digit. Initially, as with the neural networks dealt with in previous videos, the predictions are inaccurate. However, accuracy is gradually improved by minimizing the loss or cost during training. For training the model, I use the MNIST Dataset. This dataset is popular and widely used among programmers. It contains 70,000 handwritten digits that are already split into training and testing data, with 60,000 training digits and 10,000 testing digits. Each digit is a 28 by 28 pixel black and white image. Each of these images obviously contains a corresponding correct human-made label. Let's begin writing the convolutional neural network in Python with the help of Keras. First, as always, I import all the packages that I will need in order to implement the convolutional neural network. Then, I load the MNIST dataset. From where? Actually, Keras has a copy of it because of how popular it is. Also, as I previously said, the dataset is already split into training and testing data, so all I have to do is assign it to xtrain, xtest, ytrain, and ytest. Remember that xtrain and xtest are the images, and yTrain and yTest are the classes or labels for the images. Next, I reshape both xtrain and xtest to -1 by 28 by 28 by 1. What in the world does that mean? Well, 28 by 28 is simply the resolution of each of the images, and 1 represents the single color channel. The -1 is a special number that essentially tells Keras to figure out what the actual value is. The actual value will be the number of images assigned to that variable. So, the only thing that will actually change in this line is the addition of the 1 color channel, and this is added to match the format expected by Keras. Next, I applied 2 categorical to yTrain and yTest. For a complete description and explanation of what this does, see my breast cancer diagnosis video. Basically, it converts the classes in yTrain and yTest into a form readable by Keras. In the following lines, I normalize the input data by taking each pixel intensity value, which is currently between 0 and 255, and dividing by 255. In order to do this, I must first change the type of the values in these NumPy arrays to float 32, so that they can contain decimals. Then, as always, I define the model in the line model equals sequential. From here, I define the input shape as 28 by 28 by 1. Note that since we only input one image at a time, the input is 3-dimensional, whereas xtrain and xtest are 4-dimensional, with the 4th dimension being the image index. In the same line, I define 32 3x3 filters, and even though I don't explicitly write it out, Keras includes a bias, since this is the default. I also don't choose to change the default of no padding after convolution, simply because it is not necessary. Next, I add a pooling layer, and more specifically, a max pooling layer with a pool size of 2x2. There are actually other types of pooling, like average pooling, for example, in which instead of taking the maximum value in a defined area, you take the average value. In truth, there isn't all that much of a difference in the resulting performance between the two, especially for a simpler example, like the one that we are dealing with. As mentioned earlier, you can change the stride length in both pooling and convolution from the default, however, this is unnecessary. Hence, I'll use the default values. Then, I apply the ReLU activation function. After this, I flatten all the matrices into one very long list of values, where each value represents a pixel. Then, I add a dense layer with 128 inputs. So, the value of each pixel will be connected to each of the 128 neurons in this layer. This connection is often computationally expensive, especially with much higher resolution images. I also apply the ReLU activation function to each of these neurons. Finally, I add an output layer with 10 different neurons. Each of these neurons will represent a class, or more specifically, a digit from 0 to 9. I apply the softmax activation function, which is used in multi-class classification problems like this one, as discussed in the last video. Finally, I compile the model. I use categorical cross-entropy as the loss, which is used in tandem with the softmax activation function. I use the atom optimizer, which will dictate how the weights are updated during training, and I state that I want to keep track of the accuracy metric. Now we have defined the structure of our convolutional neural network. Next, I perform training in the line model.fit. I pass xtrain and ytrain cat, and I define the batch size, epochs, verbose, and validation split. For a complete explanation of all of these, see my neural network regression video. Finally, I evaluate the model and find that the accuracy is good. And that's it. I have now written a very simple convolutional neural network in Keras. With this simple dataset, there is very little that I can do to improve the model's performance, let alone by a substantial amount. For example, I could add more layers to the model, or I could implement dropout. However, none of this is necessary, and again, it doesn't have a substantial effect on the model's accuracy, which is already quite high. The next section of the code is responsible for the GUI, or graphical user interface, that you saw at the start of this video, and for the operations performed between the numbers. Basically, here's how it works. First, the program opens a window into which the user can write with their mouse. Whenever the user clicks, holds, and drags, the program will plot circles in a location corresponding to the position of their mouse. The program keeps track of every location in which a circle was plotted so that an exact copy of the displayed image can be made that will be inputted to the convolutional neural network when the user clicks Save Image. Before being inputted, however, the image is resized to 28 by 28, are the dimensions of images in the MNIST dataset. The program also makes the pixel intensity values float 32 variables and divides each of them by 255, just as we did when we trained the network. Then this slightly modified image is inputted to the network, and the program takes the digit with the highest probability in the network's output. This digit is then displayed. If the user clicks on the "Click here if the number is incorrect" button, then the program will clear the current screen and will replace the digit with a new one when entered by the user. A user at this point can either enter the second digit in a number, in which case the process will repeat and the two digits will be joined together, or the user can click an operation. When the user clicks an operation, the program stores the name of that operation in a variable. After this, the initial process is repeated and the user can enter another number. When they click equals, the program simply performs the requested operation between the two numbers and prints the result. If the user happens to click the reset button at any point in this process, then all the existing information will be cleared or overwritten, and the process will start over again. And that's it. If you want to try the program out for yourself, you can download the code on my GitHub, for which there is a link to in this video's description. Note that if you do so, you will need to install Pillow in your virtual environment. This is done with the following command. And that's it. We now have a basic functional calculator that can recognize handwritten digits and perform simple operations between them. In case you didn't already know, this video is part of a series in which I find really cool datasets like this one, and for each of them, I show you how to implement a neural network. In doing this, I hope to both entertain and educate you. Subscribe and click on the notification bell to be notified when I release a new video, and also hit the like button and leave a comment if you want this video to reach more people. Thanks for watching.